This is Free Range Digital Design Foundation Modeling, Chapter 23. We've been working with state machines, and what we've been doing is designing counters as a way to learn the underlying structure of state machines, and we'll be continuing that in this lecture. Once again, the purpose of state machines is essentially it's hardware that controls other hardware. So it's a circuit that controls other circuits. State machines are very structurally simple. Essentially, it's two decoders and some registers. And as we develop these, we're going to be kind of developing at a medium level and develop an intuitive feel for these, and then kind of abstract it in later chapters to a higher level. This is our general circuit here. These modules represent combinatorial, sequential, and peripheral elements that are all speaking to each other, trading data under the control of something, either a state machine or microcontrollers. Now, in this text, we are controlling circuits with a state machine, which is hardware. Microcontroller is necessarily firmware or software. It's certainly a topic for another course. So this is our first example problem. It's very similar to previous problems that we've done in that it is a counter. It's an up counter. It's a Stone Age unary up counter. So it's this 3-bit output here is actually Stone Age unary. And also it has a count enable. We've seen that before. And the new thing in this circuit, it has a ripple carry out. Ripple carry out indicates when the counter has reached its terminal count. Now, in this case, the count we're working with is this. So this is a 3-bit Stone Age unary count. This is considered essentially 3, so that's going to be the terminal count. And so when this counter reaches its terminal count, this RCO is going to turn on. For all the other 3 values here, it's not the terminal count, it's going to be off. And so we need to design that into the circuit as well as indicate that in the state diagram. So the first step here is a state diagram. So let's crank this out. There's 4 different possibilities here. That means I'm going to need a register that's 2 bits wide to represent these 4 possibilities. That means with 4 possibilities I have 4 states, and so let's draw those states. These are the basic states. We can add some transitions now. When the count enable is turned on, this transitions normally. When the count enable is turned off, indicate the count enable is not asserted or turned off with the bar over the CE with the count enable. We need one more thing in the circuit. We need to indicate the RCO. Now the RCO is going to be turned on in one state. It's going to be off in the other state. So the state it's turned on is in the terminal count right there. But we need to indicate what that is in the other states. I know I ran out of room here. And so I am indicating that RCO for all the other states is turned off by putting it inside the state bubble and putting a bar over it. So that looks good. We're going to call this state diagram done. The next step, I guess there's a couple next steps so we can kind of sort of draw what we know about the underlying modules. We know there's going to be certainly state registers in this. We know it's 2 bits. We know it's going to feed around into a next state decoder. And what else do we have in here? We have a count enable going into this next state decoder. And we should list this as a 2 just to be clear. That's the guts of this thing. So we have 2 things we need to do here. We need to handle the next state decoder, and we need to handle, this is going to have an output decoder. We'll go ahead and draw that. Like we're almost done. Let's go ahead and give these a name. This is going to be the state, and this is going to be the next state. What we need to do first is define this next state decoder. If we look at this, it has 3 inputs. We're going to kind of brute force this with tabular format. That's going to be a table with 8 rows in it, and so we're going to do this kind of special. And the output of this is going to be ST plus. Now this is the present state, and this is the next state. I've drawn this table kind of special. It's a little bit messy. I'm going to fix that. And so what we have here is these two bits are the state. And if you look at these two bits, they come in pairs. The state come in pairs by the way I set the table up. So this is actually kind of an intelligent way to set the table up. I'll show you why in a minute. So let's fill this table out. So if I'm in state 0, 0, and the count enable's turned off, I go to state 0, 0. If I'm in state 0, 0, the count enable's turned on, I go to state 0, 1. If I'm in state 0, 1, count enable's turned off, I stay in 0, 1. Otherwise 0, 1 turned on, I go to 1, 0. Okay, so it's 1, 0. You can see a pattern here. 1, 1, 1, 1, 0, 0. And so that is our next state decoder definition. It's a table. It's used to define this box right here. The output is a little bit different. There's only 2 bits on this, the input to this output decoder, which means we use a tabular format. It's only a 4-row table, so it's based on the state. Both these outputs are based on the state. And so let's do that. ST. When I'm in state 0, 0, we're going to associate that with count 0, 0, 0. And the RCO is not at its terminal count, so we'll say 0. Here's 1, still not terminal count. There's 2, still not terminal count. And there's 3, which is the terminal count, and that's when we're going to turn the RCO on. So this right here is the output decoder definition, which defines this box, of course. And I think at this point we are done with the circuit. Notice that these states are somewhat arbitrary. What's important is this count comes on the output. You can actually put these states in another order. It's just handy to put them in increasing order like that because we're used to working with binary in that fashion. And check this circuit out. I don't have anything to do to it. I'm going to call it done. Here's an associated timing diagram with this. You can see that here is the count enable, so this is just an increment. Here is the terminal count, and you can see when the output is 1, 1, 1, this RCO in fact turns on, and in every other case that RCO is turned off. You can also see here's a hold condition because these two values don't change because the count enable is turned off. Here is a massively important example problem. This represents state machines as hard as they possibly can get, and it doesn't get any harder than this. So it is kind of a little bit strange, but let's crank through this. So this is very similar to the last problem, except I don't have an RCO, I have this binary count. So the Stoney's unary count is exactly the same, but now we have a binary count output. And the issue with the binary count output is that this binary count output is dependent upon 2 things. It's dependent upon both the state and both the count enable. So what the problem says is when the count enable is asserted, you get a binary count. If the count enable is not asserted, the output's 0. So we need to represent that in both the output decoder and the state diagram. And so first of all, for this problem, we'll do the state diagram. It's going to be a little bit different, and this is, like I said, it's as complicated as it gets. So I'll do the normal stuff, and then we'll fill in the details. Okay, so we're at the point where this problem looks like the last problem. It doesn't have an RCO, but we have another issue here. Now the issue here is the count is always a function of the state, and so I put that in the bubble because the bubbles are known as state bubbles. But what happens here, the other output, which is the B count, the binary count, is a function of 2 things. It's a function of state, and it's a function of that CE input. So the idea here was the CE is not asserted, the binary count goes to 0. If CE is asserted, the binary count is a normal binary count. Now, so we got to represent that, the output, not inside the bubble, but outside the bubble. So what we're doing is representing that binary count next to the CE input. Now the CE input determines transition, so it's a little bit confusing. It looks like we're associating that the binary count with the arrows going to this state, blah, blah, blah. It's really not the case. So let's draw this in and then we'll have some more comments on this. So in this 0 state, if CE is not on, the B count, VCNT equals 0, 0. Okay, if it is on, not too exciting. Okay, but here's the difference. In this 1 state, what we have here is, we're going to put a slash there, so this is input, and we're going to fill in the output. VCNT equals 0, 1, but if this count enable is not asserted, the B count, the binary count is equal to 0. This is very confusing. It's really like the hardest thing about state machines is this output here is associated with the arrow. The arrows are associated with the state the arrows are coming from. So this arrow is going to this state, but this binary count here is associated with this state, as is this binary count. So you're going to see this in every case, that when the count enable is not asserted, when the count enable is not asserted, the binary count is 0. When it is asserted, the binary count is a normal count. So here's a normal count. This is 2. Once again, we have to represent the output. This output is now a function of the input, so we put that output next to the input. It looks like this arrow is going to this other state here. This output is associated with the state the arrow is coming from. So that goes for both of these and all of these. So it's a little bit more confusing, but let's keep going on this thing. I'm going to draw this circuit here. This is what you would expect. It's going to be a little bit different than the last couple examples we did, because the output, namely this B binary count, is a function of the input, which is CE. So we need to put that CE onto the input of this decoder here. This is our final circuit diagram. What we need to do is define both decoders. And so let's do that. Now, in the previous examples, we had two different tables. We had a table for the next state decoder, and we had a table for the output decoder. In this problem, it gets a little bit longer, but we're going to combine those tables to one table, and it's going to simplify a little bit. So I'm going to go ahead and draw that table, and I'm going to draw the next state version of it, and then we'll talk about the output. The next state version is exactly like the previous example, so I'm going to speed through it. There's the next state decoder as you saw it in the previous problem. In this problem, very similar to the last problem, the SB count, the Stone Age binary, Stone Age unary count is still the same, so we'll go ahead and fill that in. And so the issue is, now that we're combining tables here, Stone Age unary count is based on the state only, and it's the present state, it's not this state. So you can see that what I'm going to do here is the way I've drawn it, once again, these states come in pairs. So that's going to be 0, 0, 0, 0, 0, 0. Here's 0, 1, 0, 0, 1, 0, 0, 1. Here's 1, 0, which is 2, 0, 1, 1, 0, 1, 1. And the last one is 1, 1, 1 for both. That's normal. That's exactly like the last problem. The difference is the binary count. There's different ways to do this, but what I like to say is that the binary count is 0 anytime the CE is off. Okay, here's the CE. So I'm going to go ahead and fill these in. Anytime the CE is off, the binary count is 0. Okay, I'm done with that one. Now anytime the binary count is on, it's a normal binary count. So here's CE equals 1, 0, 0. Okay, CE equals 1 is 0, 1. CE equals 1 is 1, 0. CE equals 1 is 1, 1. Now the difference, this is completely, significantly huge point here. The difference of these problems is you can see that this output, this SB count, is only dependent on state, so it doesn't change in the middle of the state. So per any given state, the output's the same. Here's the binary count. Since the binary count is a function of the CE input, it can change anytime the CE input changes. So it's a function of state and the CE input. So you can see in these cases, it changes even though the state's the same. So the state's the same, yet the binary count output changes. So this is super significant. These are the two separate types of outputs in state machines. And this is called a Moore output, and this is called a Mealy output. Good name, by the way. Just joking. The super important point, we'll land on that later in more detail. So there's a significant difference in the timing diagrams for these two machines. So in this diagram, B count is a function of the CE input, so it can change anytime the CE input changes. Now this is different from SB count, in that SB count is only changing when the state changes, but the binary count, the B count, can change anytime CE changes, and that's what you see here. For example, in this setup right here, it's changing because CE turned off right in the middle, turned back on, of course, but it changed in the middle, so that this output reacted to the inputs, the Mealy output reacted to the inputs, the Moore output did not react to the inputs. The Moore output is only a function of state, whereas this B count, which is the Mealy output, is a function of both state and the external input, which is CE.